So here are three problems with the basic binary tree traversal is pre-order, post-order, and in order. So it is pretty simple and naive just to do it the recursive way, but we will do it anyway. Then we'll move to the fun stuff, which is the iterative way. We'll just do the iterative, the recursion way real quick. So return. Then it will be so that should be it for the recursion way. So sanity check, and for each recursion we have a empty list, and we append the current node, and we set the first one, the left one, the right one, and we extend it to the current order. The left one, the right one, so we have a pre-order, pre, left, right, and we return the order. And we submit it. Okay, it works. And for the other two, we just copy paste. So basically, all we have to do here is just move this value right here, since this is post order. So we'll do it like this. So it'll be left, right. Oops. Okay, this should be post order here. Okay, submit. Okay, it works. And for the third one, same mode, same mode. Oops. We just copy this, and we have to change this. So it will be in order and in order. And for in order, we want left, mid, right. So we move this line to here. And we submit. All right, it works. So now we move the recursion out of the way. Let's move to the fun stuff. So initial code template. So the easiest one is the pre-order. Like the graph here, pre-order, basically we can just use a stack, and we visit the first one, we track the current value, and we record its two children and the first one, and we will adopt a stack data structure. And because it's stacked, it will follow the last in, first out. So the rule, and then it will visit 4 and 5 before it reaches 3. That's exactly what pre-order is, which is 1, 2, and 3. So, and it will follow the order here. First we have 1 and 2, 3, and 2, 3, 5, 4. You can see it's pretty DFS, and a stack definitely can do the trick. And let's try to implement it. So we start off with the sanity check. If not, then return empty since you have nothing. And since this is a stack, you have stack, and initially you only have root on it, and order is the final result we want to return. And while stack node equals to stack.pop, and once you pop it off, since this is a pre-order, we want to record the current value, so it gets the pre part first. So it will be order.append node.val, and then we'll move to the two sides. So if node.left, so if there's something on the left, then stack.append node.left, and if node.right, and stack.append node.right, and return order. It may look correct at this moment, but there's a huge caveat right here, is that since we're adopting a stack data structure, it is last in and first out, and we want to do the pre-order, which has the order of mid, left, right. Since we already have the mid down here, we actually want to reverse the order of these two, so we can have left to be the last one inserted into the stack, which will be the first one to pop out, so it will follow right after mid. Therefore, we can have a mid, left, right order, which is pre-order. So let's do a quick sanity check. We first check if it's a empty node. Is nothing. Then we return empty, and we do the stack. Put the initial root on it. Looks correct, and this order is our return result. And while there's something on the stack, we pop it off to get the current node, and we get the current value, which is the mid part or the pre part. And if there's something on the right, we add it to the stack, and if there's something on the left, add it to the stack as well. And lastly, we return the order. Let's run a test here. So it works, and it works here as well. So in terms of the time complexity, the stack will be of space, at worst will be space of how many nodes we have in the tree. And for this, basically this is a DFS, and a DFS we have a time complexity of O of V plus E, which V being the number of vertex, or in this case nodes, so O of, have a big O of V plus E, with V being the number of nodes and E being the number of edges. And that's it for the iterative version of pre-order traversal. Now let's move on to the post-order traversal. Let's set the initial template. Now for the iterative approach, and we can see here the post order of it is left, right, and the current. So left, right, current, and left, right, current, and the current. So what we actually want to do here is we want to sort of adapt the code here of pre-order and somehow transform it into something that we can output for post order. And the way we're going to do that is, you can see pre-order is cur left right. If we can somehow make it cur right left, you can see it is a perfect reverse version of the post order one. And we can see here, if we do left right cur and a reverse version of this guy right here, we will have left right cur, which will be the same. And let's try to implement that, and it will be very similar to the previous code right here. And let me show you how we can actually make that work. So this part remains the same for this part, and the same goes for this part. However, here we have to sort of reverse the order like the previous caveat we have, and it will be left right. So right now with this, it will be mid right left. And if we return the reverse version of the order, now it will be left right mid, which is exactly what post order is. And you might ask, if this is simply the way we can do it, does it actually work, and how do you prove it? I cannot provide a substantial mathematically sound proof, but by looking at a graph, you can see they follow a symmetrical route. And for example, for post order, you have left, right, cur. So finish the left side, left, right, cur, and then lastly you have this. And for the reverse version of cur right left, first you have left, right, cur, and left, right, cur, and cur. You can see they're actually symmetrical. So by doing the reverse of the order, you can actually conveniently get the post order result we want. Since we only do a string manipulation here, it will have the same runtime over v plus e like before, with v being the number of nodes and e being number of edges. And lastly, let's move on to the in-order traversal. Let's get rid of the recursive version. Let's move on to the iterative version. And here you can see we have a node here, and basically in order we want to do left, mid, and right. So we can see we'll prioritize everything on the left, and we will keep going left since the leftmost node will always be output first. And following that same logic, we'll introduce a dummy node so we can do a operation, which is first we go right one node, and then we keep going left. And the benefit of this is, at the previous step, we can output the left node, the leftmost node from the stack, and we can print it or add it to the order, and we don't have to worry about it because it will always print it out and everything on the right of it can guarantee that it will be printed or added to the order later than that. So let's try to do that. And first we have a sanity check. And the dummy node, like we said before, dummy equals to pre-node 0, and dummy dot right equals to root, and at first on the stack we have dummy. The order will be the output. It will be empty at first. So we'll do while stack. So there's something on the stack, and it will follow the last in first out, since that's what we want. Since the 4 is always output before the 2, since this is the in order. And while stack, and first we'll get the parent node. So stack dot top, and if node dot right. So like we said before, we'll first go right one step, then we keep going. Since this stack, ideally it would always be printed out before this. So at this step, we're assuming everything is done from here and the left. We're already done with that, and we'll get to the right wing of that node. So if right dot node, there's something there, so node equals to node dot right. And once we're in the right tree, we want to prioritize everything on the left side, and we want to add all those to the stack because we want to handle those first, no matter if it is popping or added to the order. And while node stack dot append node, and node equals to node dot left. So we'll keep going left until we can't. And now if there's something on the stack, and there's something on the stack because we keep going all the way left, so the current last item on the stack is guaranteed to be output at this stage, since the leftmost node from pre-order traversal is always to be output first. So if stack, then we will add that to the order, stack the last one, and the value of that. Okay. And once we're done with these, we can simply return the order, and we can do a quick sanity check here. So this is check if root is none, and the dummy node, like we said before, and the dummy to right is the root. And because it's dummy, everything about itself and on its left subtree is handled. Itself doesn't have to be handled, and the left subtree is basically non-existent, so we can focus on the right tree. And stack initially only have dummy, and the order is the output value, while stack currently only have dummy, and like we have here, initially you only have dummy, then by going one step right, and we will have 1, 2, 4 in the order of 4, 2, 1. And at this stage we'll print 4. As you can see here, 4 should be the leftmost. 4 is the leftmost node in the graph, and it should be printed first. And then we move to 2 in the graph, and it will be add to the order since 4 doesn't have any right subtree. And then we add 5 and 1, and just keep going. And you can see here the way we write the code, the print, which is the order append, is always going to be one step ahead of the pop, since we use pop to access the right subtree, and by doing that, we're assuming everything is done with itself and the left subtree, which it is since we have already printed this one. And by printing this one, we are saying that everything on the left, since it should be printed before this, it should be done. So that's why we have a one sort of offset here. And let's try to do a test run. And it works. And let's try to submit it. It also works. And let's talk about the space and time complexity. Since we're using a stack here, so the worst case scenario would be everything's on the stack. So it would be all of V for space complexity. And for time complexity, since what we are doing here is actually, let's see, just run through the entire graph in a sort of left-oriented fashion, but in essence, we just run through all the nodes and the edges. So like before, it will be of all of V plus E, where V is the number of nodes or vertices and E is the number of edges. And that's it for this series. It's actually pretty fun doing the iteration way instead of the recursion way. And it does make sense for all three of them have the same time complexity. Otherwise, one should be preferred than the other two. And that's it.